So have you ever stopped to wonder how an app like Netflix can serve, hundreds of millions of people all at once without just completely falling apart? It's not magic, I promise you. It's actually a series of really brilliant solutions to some incredibly complex puzzles. Today, we're going to dive into that beautiful chaos of modern applications. We'll demystify the biggest challenges and pull back the curtain on the elegant patterns that make massive, massive scale possible. All right, let's get into it.
Here's our game plan. We'll start by really getting a feel for why modern apps are so tricky to manage. Then, we're going to solve two huge puzzles. First, how to track a single click through a whole maze of services. And second, how to make a process wait for something that might happen minutes or even days from now. And then, the best part. We'll see the incredible payoff and how these solutions unlock pretty much infinite scale.
Okay, first things first. Let's set the stage, because our story really begins with this fundamental shift in how we build software today.
See, in the old days, applications were often built as one single giant block of code. We call that a monolith. And if any one little part failed, well, the whole thing could just crash and burn. And updating it, forget about it. It was a huge, risky operation. So the modern approach is to break that giant block apart into a team of independent specialists.
And this approach has a name: microservice architecture. Just think about an e-commerce app for a second. You've got a service for user profiles, right? Another one for processing payments, and maybe a third for managing inventory. Each one is built, deployed, and scaled totally on its own. And that independence, that's its superpower. It lets teams move way faster and makes the whole system a lot more resilient.
But, and this is a big but, here's the catch. When you click that buy button, that one single request might bounce between 5, 10, maybe even 50 of these little specialist services. So if something goes wrong somewhere along the way, how in the world do you find it? It's like trying to trace one person's path through a massive, chaotic city with no street signs. And that, right there, is our first big puzzle.
To solve this madness, we need a way to follow the path of that request. We need, well, a kind of digital breadcrumb trail.
And this quote from Microsoft's own engineering team just nails the problem. Each of those little services creates its own log files. Without some way to connect the dots, trying to trace a single transaction is an absolute nightmare. The business cost here is real, too. We're talking longer outages, frustrated customers, and engineers pulling their hair out.
The solution is actually surprisingly simple, but it is incredibly powerful. It's called a correlation ID. The best way to think about it is like a passport. The moment a request enters your system, you stamp it with a unique ID. That passport then gets shown at every single service it visits, and each service logs that ID right alongside whatever it's doing. Now, for this passport system to actually work, there are a few golden rules you just can't break. The ID has to be assigned the second a request hits the system. It has to be passed along in the header of every single call. And, of course, it has to be logged at every single stop. If you stick to these rules, you suddenly gain a superpower. You can instantly see the complete end-to-end journey of any transaction. And just like that, puzzle number one is solved.
Okay, so we can track a request now. That's awesome. But what happens when one of our services needs to wait for something to happen? Something that's kind of outside of its control and might take a really long time.
This brings us to puzzle number 2, the asynchronous waiting game. You see, in a simple, synchronous world, you'd call a service and just wait. Your process would be totally frozen, hogging resources, doing nothing. It's super inefficient. Modern scalable apps have to rely on asynchronous communication. You make a request, and then you just move on, with the promise that you'll get a notification later when the job is done. This is absolutely essential for performance, but you guessed it, it creates a whole new problem. This question from a developer on Stack Overflow just perfectly captures the dilemma. Their start function kicks off some external process. That process is going to send its result back later, using something called a webhook. But how does the original start function get that result? It can't just sit there and wait, because it would eventually time out and crash. It's a classic problem.
So what's a webhook? It's really just a notification. Instead of your app constantly bugging some external service, asking, "Are you done yet? How about now? Are you done yet?" The external service just promises to call you back at a specific web address as soon as it's finished. It's pretty much the standard for this kind of async communication.
So, how do we solve this whole waiting problem without freezing up our application? Well, we use this really elegant design called the pause and resume pattern. Let's walk through this. Imagine it's like a coat check at a fancy restaurant.
First, your process, your workflow, registers with a central portal and gets a unique ticket. That's the session ID. Second, your process just pauses. It goes into a dormant state, not using up any resources. Then, maybe much later, an external event happens. The webhook arrives at the portal holding that ticket. The portal looks at the ticket and figures out exactly which pause process it belongs to. And finally, it uses a special resume link to wake up the exact right process, handing it the new data. And the process just picks up right where it left off, as if no time had passed at all. It's brilliant.
So, we've solved tracking and we've solved waiting. Why is this such a big deal? Because mastering these patterns is the absolute key to unlocking massive scale and delivering real business value. This is where it all comes together.
You see, true scalability relies on these core principles, and our two solutions are the keys that unlock all of them. You can't do effective load balancing if you can't see where your requests are going. That's what our correlation ID gives us. And you can't have truly decoupled asynchronous messaging without a reliable way to handle long waits. And that is the job of the pause and resume pattern. These aren't just technical details. They are the absolute foundation for growth. And if you want proof, just look at the numbers. Netflix serves over 260 million subscribers by applying these exact principles. They actually moved away from a monolithic system for the simple reason that it couldn't handle this kind of load, and it couldn't let them innovate as fast as they needed to. In fact, Netflix had to build an entire suite of their own tools just to manage this complexity. Look at this list. Eureka helps services find each other. Kafka manages these huge streams of asynchronous data, which totally relies on patterns like pause and resume to work. And Atlas provides the monitoring that's only possible when you have robust tracking, like we saw with correlation IDs. They solved these exact puzzles, and the payoff was, well, a global entertainment empire.
So here's the real takeaway. Modern applications are, by nature, complex. But that complexity isn't a bug, it's a feature. It's what gives us flexibility and resilience. The secret isn't trying to avoid the chaos, but learning how to tame it with smart, proven patterns like the ones we've talked about.
By solving these foundational problems, you're not just fixing bugs. You are building a platform that's ready for growth, a system that's maintainable, observable, and ready for whatever the future decides to throw at it. So the only question left is, what are you going to build with it?